morning, friends. Already we discussed the two illustration 15.2 and 15.3. Now 15.4. This illustration is to find out the speed of the sound wave in A medium at STP. The question is that estimate the speed of sound in A at standard temperature and pressure. The mass of the one mole of an A is 29 into 10 raised to minus 3 kg is given. Here, the mass of one mole of an A is given 29 into 10 raised to minus 3 kg. Now we know the Newton's formula for the speed of a sound wave. V is equal to under root of pressure upon density of the medium. For that purpose, first we have to find out the density. Density is equal to mass upon volume. Mass of one mole of an A is given. Here we have to find out the speed of a sound wave at STP. Therefore, at STP, standard temperature and pressure, volume of one mole of gas is V is equal to 22.4 liter. This liter is converted into meter. 22.4 into 10 raised to minus 3 meter cube. Relation between the liter and meter is 1 liter is equal to 10 raised to minus 3 meter cube. Okay. And pressure is at STP, pressure P is 1.1 atmospheric pressure, 1 atm. Therefore, 1.1 into 10 is to 5 Newton per meter square. Newton per meter square. That is the pressure at STP. Therefore, the density of an air at STP, therefore, at STP, the density of an air is rho is equal to mass upon volume. Mass is already given 29 into 10 raised to minus 3 upon volume is 22.4 into 10 raised to minus 3. It is simplified, we obtain 1.29 kg per meter cube. Kg per meter cube. Now, speed of a sound wave in A is V is equal to under root of P upon rho, pressure upon density. Pressure we already know that 1.01. Therefore, we substitute the value 1.01 into 10 raised to 5 upon density is 1.29. 1.29. As is simplified, we obtain the answer is 280 meter per second. That is the speed of a sound wave in A medium at STP, standard temperature and pressure. Very easy numerical that may be asked for the 2 marks question. Or on the basis of this question or this numerical, the objective question may be asked. Again, they estimate the speed of sound wave at standard temperature and pressure in A medium. The mass of one mole of an A is 29 into 10 raised to minus 3 kg. Mass is given 29 into 10 raised to minus 3 kg. And already we know that at STP, the volume of one mole of gas V is equal to 22.4 liter. Convert into meter. 22.4 into 10 raised to minus 3 meter cube. And pressure at STP, P is equal to 1.01 atm. Convert the atmospheric pressure into the Newton per meter square. So 1.01 into 10 raised to 5 Newton per meter square. Now from Newton's formula we know that the speed of a sound wave in a medium V is equal to under root of pressure upon density. Therefore, here the value of the density is required. Therefore, first we find out the density. At STP, the density of air is rho is equal to mass upon volume. Mass is 29 into 10 is to minus 3 upon. The volume is 22.4 into 10 is to minus 3. Therefore, the density of air medium is 1.29 kg per meter cube. Now, the speed of a sound wave in a medium is V is under root of P upon rho. Value of the pressure is 1.01 into 10 is to 5 upon density 1.29. As we simplify, we obtain the speed of a sound in a medium is 280 meter per second. Now the next numerical is 15.5. A pipe 30 centimeter long is open at the both ends. Which harmonic mode of the pipe resonant with 1.1 kilohertz source? After finding the mode of harmony, we have to also find out that will the resonance with the same source be observed if one end of a pipe is closed. Take the speed of a sound in a medium is 330 meter per second. Right? Now for open pipe, the frequency of nth harmonic is Fn is equal to Nv upon 12. Now listen here, the frequency of the harmonic is given. We have to find out for which harmonic the resonance occurs. Here the frequency Fn is given the 1.1 kilohertz. Fn is equal to 1.1 kilohertz. That means the 1.1 into 10 is to 3 hertz. Number of mode we have to find out N. V is given 330 meter per second. Length is given 30 centimeter. That means the 0.3 meter. 0.3 meter. Substitute this value. Therefore, 1.1 into 10 is to 3 is equal to N. V 330 upon 2 into 0.3. 2 into 0.3. Thus, we obtain the value of N is equal to second. So, in case of an open pipe of 30 centimeter long, the harmonic mode is obtained at 1.1 kilohertz is the second harmonic. Right? Now, thus the resonance will produce with the second harmonic. Thus, the resonance produce with second harmonic. Now we have to also find out this resonance for this frequency, what are the resonance take place in closed pipe if the one end of this open pipe is closed. Right? Now, one end of open pipe is closed. Right? Therefore, it becomes the closed pipe. It becomes closed pipe. And we know that in a closed pipe only the odd harmonics are possible. So first we find out the frequency of the first harmonic. Right? The frequency of first harmonic F F1 dash is equal to V upon 4L. V is given 330 upon 4, L is 0.3. Therefore, for the first harmonic, the frequency is 275 Hz. 275 Hz. So in a closed pipe, the first harmonic is obtained at 275 Hz. We have to find out this frequency 1.1 kilohertz is obtained in closed pipe, and if obtained, so for which harmonic? Okay. Now for closed pipe, only the odd multiple harmonics are possible. Therefore, the frequency are its frequencies Fn dash is equal to n dash F1 dash is equal to 2n minus 1 F1 dash, where the n is equal to 1, 2, 3, and so on. And n dash is equal to 2n minus 1. Is the order of harmonic is equal to order of harmonic. Because in closed pipe only the odd harmonic take place, therefore n dash is equal to 2n minus 1. It is substituted here too. So 4 minus 1 third harmonic. As we take the 3, 6 minus 1 fifth harmonic, therefore odd harmonic are obtained. So different value of the possible harmonic, different value of frequency of possible harmonic are Fn dash is equal to F1 dash, 3 F1 dash, 5 F1 dash, and so on. So as you multiply the F1 dash 275 with 1, so first harmonic with 3, third harmonics with 5, fifth harmonic. Therefore, the frequency I obtained for the first harmonic 275 Hz, second 825 Hz, for third 1375 Hz, for fifth, for seventh 1925 Hz. None of above frequency is matched with the 1.1 kilohertz. So resonance will not take place in case of a closed pipe. None of above frequency matches with 1.1 kilohertz. So the resonance will not take place. With closed pipe. So in short, as we close the one end of the open pipe, the resonance does not occur with the same frequency. Again, that is the very interesting numerical, but very easy. Only we have to information about the frequency of the harmonic. Here, a pipe of 30 centimeter long is given. That is the open at the both ends. The which harmonic mode of the pipe resonant with the frequency 1.1 kilohertz. So first, in case of an open pipe, we have to find out the mode of oscillation. For an open pipe, the frequency of the nth harmonic is Fn is equal to Nv upon 2L. Fn given, V given, L given, we have to find out the N, therefore N is equal to 2. So for given frequency, thus the resonance will produce with the second harmonic for a given frequency. Now, the one end of a open pipe is closed, so it becomes a closed pipe. Right? The frequency of the first harmonic for closed pipe is F1 dash is equal to V upon 4L. So frequency of the first harmonic in case of a closed pipe is 275 Hz. Now for the closed pipe only, the odd multiple harmonics are possible. Its frequencies are Fn dash is equal to N dash F1 dash is equal to n minus 1 F1 dash. Here the value of n is 1, 2, 3 and so on. N dash is equal to 2n minus 1 is equal to order of odd harmonic. Therefore, the different value of the frequency of the possible harmonics are Fn dash is equal to F dash, F1 dash, 3 F1 dash, 5 F1 dash and so on. As we multiply the F1 dash 275 with 135, so frequency obtained 275 Hz, 825 Hz, 1375 Hz, 1925 Hz. None of the above frequency matches with the given frequency 1.1 kHz. Therefore, the resonance will not take place in case of a closed pipe for the given frequency. Clear this? Illustration 15.6. The two sitar string A and B playing the note Da are slightly out of tune and produce the beats of the frequency 5 Hz. The tension of the string B is slightly increased and the beat frequency is found to be decreased to 3 Hz. What is the original frequency of the B? The original frequency of the A is 427 Hz are given. Right? For that purpose, first we consider the original frequency of wire A and B are F A and FB. Right? Now, suppose the original frequency of wire A and B are Fa is equal to 427 Hz already given. Now initially wire A and wire B produce the 5 beat per second. Therefore, the frequency of the B must be the difference of the 5 with 427 is FB is 422 Hz, or FB is equal to another difference with the 427 is 432 Hz. Because initially the wire A and B produce the 5 beats per second. Beats is the difference of the frequency, Fa minus Fb. So here 427 minus 422, 5 bits are produced. Here Fa minus Fb, again the 427 minus 432, 5 bits per second are produced. Right? The reason is that because the initially they produce, well, they are 5 bits per second between A and B. Therefore, we consider the value of possible value of B is 422 or 432. Right? Okay. Now, the tension increase. As the tension in B slightly increased, therefore the frequency will also increase. As the tension of YB increased, so the frequency of wire B is also increased, and this frequency is FB dash, FB dash, which can produce the 3 bits per second with A, which produce 3 bits per second with A. So we can take FB is equal to, here 427 is FA is given. Now the difference for the bit produced per second is 3. Therefore 427 minus 3. 427 minus 3. Already we have the FB is 422. 422 hertz. FB and FB dash is equal to 424 hertz. So that FB must be greater than the F dash B must be greater than the FB. Because as the tension wire B is increased, therefore the frequency increased, therefore this frequency must be greater than the original frequency of the wire B. Initially, there are the 2 possibilities of the frequency of the wire B. One is 422, second is 432. As we consider the initial frequency is 432. Now we increase the tension in wire B. Frequency of wire B is also increased. Therefore, FB dash must be greater than the FB. So as we consider the initial frequency of the B is 432, so that is not possible. Therefore, the initial frequency is 422 hertz. Right? So FB dash is greater than FB. Therefore, FA minus FB. FA is 427, FB 422. Therefore, 5 bits per second. And FA minus FB dash. So it's equal to 427 minus 422. Right? 424. Therefore, 3 bits per second are produced. Clear this? Here, this numerical is quite logical. First, the frequency of A is given. We have to find out the frequency of B. Here, the difference between the frequency, that means the beat produced per second, are given. That is the phi. Here, FA is given. So we know that the FA minus FB is equal to phi. Therefore, FB is equal to FA plus or minus phi. Therefore, 2 possible values of the B are take place. One is 422, second is 432 hertz. Right? Now, as the tension of wire B is increased, so what's happened? The frequency of the B is also increased. Therefore, the new frequency is FB dash. FB dash must be greater than the FB. Initially, FB are 422 and there is the 432. After applying the tension, the 3 bits are produced per second. So frequency of the A is 427. So now another possible value of FB are, one is 424 and second is 430 is 430. 430 is less than 432, therefore that is not possible. Therefore, the FB greater than FB, FB dash is greater than FB, therefore FB dash is 424 is possible. As we consider the FB dash is 424 and FB is 422, so question is right, that means the FA minus FB. So for 422, the 5 bits per second are produced. And as you consider the FB dash is 424, so 3 bits are produced after the tension increase. Clear this? So there is a illustration of this chapter are completed. Now in next lecture we start our numerical exercise.